We have been discussing fully differential op-amps. Fully differential op-amps, fully differential circuits, you can sort of derive them by combining pairs of single-ended circuits. The difference, of course, is that fully differential circuits are expected to have common mode rejection. It's not the same as just putting two single-ended circuits next to each other. Okay. And to make fully differential circuits using op-amps, we need fully differential op-amps, and that's what we have been discussing. So every one of the op-amp types, like single-stage op-amp, two-stage op-amp, and so on, or any number of stages, will have a fully differential counterpart. Okay. So typically, the first stage is anyway a differential pair, even in single-ended op-amps. And after that, you will have either pseudo-differential stages or fully differential stages. The pseudo-differential stages, the advantages, they have a higher swing, whereas fully differential, differential amplifier typically has a lower output swing. Now, a key element of any fully differential circuit is common mode feedback. This is to make sure that all the advantages of this differential operation come from signal having two components which vary in equal and opposite directions. To enforce that, you need common mode feedback. And of course, the common mode feedback must be such that the following stage is biased correctly and so on. So the common mode feedback, there is nothing special. It's another feedback circuit. So for instance, a fully differential circuit has two inputs and two outputs. So whereas a single-ended feedback circuit has one input and one output. So you have two feedback loops, but you don't think of them as independently for two inputs and outputs, but for the differential mode and the common mode. The differential mode defines the functionality. The common mode typically sets the bias value. Okay. Now, to analyze these, we have differential and common mode half circuits. So the common mode half circuit of the common mode feedback, that is another negative feedback loop. So knowing what you know about negative feedback circuits, you can analyze them. Okay. Typically, many of the common mode feedback circuits that we have seen correspond to either one amplifier or two amplifier stages in feedback. Okay. So the same rules apply for the loop gain, for the step response to be well behaved, etc., etc. In simulation, you will have to check the behavior with both differential excitation and common mode excitation. Okay. You will have usually abbreviated to CMFB, and this basically enforces and also okay. So every one of the op-amp types we can convert to fully differential behavior. Okay. So I'll just give an example, but so far the type of circuits we have seen are, for each amplifier we have a separate common mode feedback stage. Basically, the idea behind common mode feedback is, as usual, you have to find some way of controlling output common mode. Okay. So typically there will be something, for instance, the gate voltage of this current source load that will control the output common mode of that load and so on. But if not, you have to add some control. Okay. You may have to add some particular way of controlling it. And you use a negative feedback loop, control the output common mode. Okay. So far we have been for a differential pair, all high gain stages basically look like two current sources fighting each other, right? One side you apply a signal and or maybe to both sides in some cases. Okay, all high gain stages are like this in CMOS, okay, in transistors. So one side of it you can apply a signal, the other side you can control the bias. So the same thing here. So this side using this you can control the common mode. You can use it using, you can do it using this also, or you can inject an additional current there. Okay, all of those are possible. So you can see just the number of circuits multiply, but the basic principle is the same. So we have been generally using this node to control the common mode of the first stage. I'm not focusing so much on the differential behavior here. You can easily write down the differential half circuit and analyze, and the picture will be like a single-ended op-amp or even simpler than that. Okay, maybe for this one I'll draw. So for this particular case, the second stage common mode is controlled using that. Okay, so this is what we have been using so far. Okay, and that's what you do, right? Let me keep this aside. So for instance, we had many different ways of controlling CMFB1. You can have some common mode detector here through which you control that, and then you have fast common mode feedback there, and similarly here so the output of the first stage will get stabilized to VCM ref 1, the output of the second stage will get stabilized to VCM ref. Okay. So the bottom line is, I mean, in fact, I showed the other circuit also where, which is more efficient, something like this, where you inject a current here to the tail to stabilize the common mode. But the common feature to all these is that you have a separate common mode feedback for each stage. The first stage output is stabilized and the second stage output is stabilized separately. Okay. Now this is actually a good choice. Typically, this is well behaved and so on. But sometimes there may be need for slightly more, I mean, economical circuit or something like that. Okay. So, for instance, here, what happens if you raise this voltage CMFB1? What happens to the output of the first stage? What happens if you increase CMFB1? What happens to these voltages? It will, what will happen? It will fall down, right? It's a common source amplifier from there to there. And what happens to the output of the second stage? I am only changing CMFB1. I am not doing anything here. What happens to the output of the second stage? It increases because the second stage has no common mode rejection. Okay. So it responds to, actually when you change CMFB1, it's only the output common mode of the first stage changes, that changes. But that also, because this has no common mode rejection, that will change the output common mode as well. Okay. So now one possibility, one of the possibilities is that you detect the common mode and compare it to VCM ref. and based on that, you can directly vary CMFB 1. Okay. So, that is possible, right. Now, we have to see what to put inside that. But by the way, which of these will be the plus terminal, which will be the minus terminal? The upper one, will it be plus or minus? I mean, you look at when CMFB1 increases, what happens to the output common mode voltage? It increases. So, which way should it be so that this is negative feedback? So, we should have minus and plus. So, that you have to determine every time. I mean, if you fed back to CMFB2, it would be the other way around. Okay. So, now of course, we do not feedback here. This will just be a fixed bias. Okay. So, this will be fixed. Earlier, we were fixing the current from the top and adjusting the bottom through common mode feedback. Now, the bottom is fixed and the top is adjusted through common mode feedback. Okay. This is fine. So, now what kind of an amplifier would we use here? What kind of an amplifier would we use here? So, let us see. So, normally we have been using the standard single stage op amp, which basically is and you complete the common mode feedback. Right. So, you can do that, but if you do this, what kind of feedback loop will you have? The common mode feedback loop, what type of stage will it be? What is it? It will have 3 stages. It will have 3 stages, and of course, you can stabilize the to stabilize the 3 stage op amp. What will you have to do? What will you need to add? Cap from where do you have to add it? So, maybe it will be easier if I draw the common mode half circuit of this. Okay. And this connection completes the feedback. We of course have the capacitors used for the differential op amp there. So, how will you? There are 3. This is basically like a 3-stage op amp in unity feedback. Okay. So, to make the response well behaved, what do you need to do? Where should I mean the 3-stage Miller op amp, how many capacitors did it have that you deliberately introduced? 2. So, where should be the other one? Right. Between? Which is the first stage? Drain of M3 to where should it be? From where to where? Drain of M3 to drain of? Okay, is that how it is? Drain of? Drain of MC3 to gate of MC1. Yeah, basically it will be here. I mean, it will be from here to the output. Okay. So if you think of this as the first stage, this as the second stage, and this as third stage. So basically it will be across the second and third stages. And of course, if this resistor is very large, you will have another parasitic pole there. And to fix that situation, you may need another capacitor there. Okay. So if you treat it like a three stage, I mean, if you have three stages with high gains, this is what you will have to do. Okay. Now, one of the things is, why would you use three stages normally? I mean, what's the reason for going for three gain stages? To get very high gain. Now, that may or may not be required for the common mode feedback loop, such a high gain, right? So, what you can do instead is, so this earlier we were using this single stage op amp with a substantial gain, okay, because there was only one more gain stage. Now, because there are already two other gain stages, you don't need to make this a very high gain stage. Okay. So, for instance, you can do that. So, if you do that, what will be the gain of this stage? What was the, so what was the gain of this stage? It is GMC1 by GDS-C1 plus GDS-C3. Okay. So, what is the gain of this stage? That is between this input and this output. GMC1 by, are you sure? It is close, but not exact. What is it? Yeah, let's forget GDSs. If you have some differential voltage there between these two nodes, what is the current flowing there? Half. So, basically, this gain will be GMC1 by 2 GMC3. So, it's of the order of 1. Okay. That is some fraction, right? So, now there are actually only two high gain stages in feedback. Now, there is this third stage. It will change the gain a little because this gain is not exactly 1, and it will also introduce some parasitic pole because of course there are many nodes inside that. Okay, but they will all be non-dominant poles, right? Because they are at high frequencies. The pole here will be at GMC3 by the parasitic capacitance. Okay, so basically you have two stages plus some another stage with a small gain and some parasitic poles. Okay. So what will you need to stabilize such a thing? You have two stages. What is it that you need to stabilize? So this capacitor is there for the fully differential op amp, right? So we have these capacitors in the fully differential op amp, and that will appear in the common mode picture also. So that itself, now you can see it's like a two-stage Miller op amp. Okay, so this itself may be sufficient to stabilize it. So then you don't need to put anything extra other than, of course, this you may still have to do if the resistor is large. Okay. So in some ways this is more efficient, but it's always more messy to have a single common mode feedback loop around multiple stages, because you will always end up with more poles and zeros. So if you can use individual common mode feedback circuits, But let's say you're really being stingy about bias currents and all these things. You want to really squeeze down the power. Then maybe you can use this, because after all, this needs only one error amplifier stage for the entire op-amp. Okay. So you can also have, yeah, this is basically single common mode feedback loop around 2 stages. But like I said, you would not make this a very high gain stage. You would make this a low gain stage. Okay. Is this fine? So a lot of it is, I mean, once we come to this point, the basic circuits, of course, you can analyze at the fundamental level. After that, I mean, if you open op-amp papers, some billions of them have been published. So you will see like small variants. Like when you are designing something, you notice some feature and you want to adjust for it, you will slightly alter the topology. Once you understand the basic circuits enough, you can do that. So I can't possibly list all the fully differential op-amp topologies. I will list some, and then you can mix and match, you can combine and so on. Okay. So one of the things is, for instance, one of the things that may sometimes have to be done. This can be in any uh, any type of circuit. So now let's say I have M1, M2, M3, M4, and similarly now let's take the first stage common mode feedback. For the differential picture, you will have M1 and M2 as the amplifying stage and M3 and M4 as the load. Okay. And in the common mode picture, this M3 and M4 will be the amplifying stage, right? One of the stages. And of course, whatever is inside this, right? So now, sometimes you may get into some conflict. Okay. For the differential picture, you may want some GM for these. For the common mode picture, you may want some other GM. Let's say a lesser GM. Okay. That is, you determine the GM of M3 and M4 for the differential picture, you get some value. And you determine that based on the analyzing the common mode feedback circuit. Let's say you get a lesser value. So what could you possibly do here? Is there something you can do? Without, of course, inventing like some new circuit. So add transistors in. So basically, the general idea is right. So if you want lesser GM for the common mode feedback than in the differential, it's actually quite easy to do. What you can do is, you can split, sorry, these are not the same gate voltages. You can split M3 and M4 into 2 parts. Okay. And you connect the drains together. Okay. So now one part of it could have a fixed bias and the other part gets the common mode feedback. Okay. So now as far as the load device is concerned, both of them will be in parallel and will appear in the fully differential picture. Okay. Whereas for common mode feedback, it's only the 2 devices inside that are providing GM. Okay. So this kind of stuff may have to be done sometimes, right? So because typically normally for the functionality, you design the differential picture and then you add the common mode feedback loop on top of it. So the GM that you have, especially in this case, in the second stage, you may use very large transistors here and you may end up with a very large GM in this case, which you may or may not want. Okay. So if you don't want it, you can reducing it is easy. That is, you split these transistors into two parts. That is, let's say this could be 0.4 and this could be 0.6. But whatever it is, of course, it has to be the same and same on the two sides. And you provide common mode feedback only to a fraction of the device. Okay. So these are all tricks that you can use, and once you get used to the circuits, you can do this yourselves. Okay. Any questions here? Ah. No, no, no. I mean, you have only one. You don't need a separate one for the first stage, right? That's the whole idea. Normally, you can use one here and one there, controlling this separately. Now, this will stabilize the, see, you have some current here. If the feedback loop is operating correctly, the gate voltages of these two will be stabilized to the correct value, which is VDD minus VSG of these devices at this bias current. Okay. And the gate voltage of this will be stabilized to VDD minus VSG for the first stage current. Okay. So the same feed, once you have it in a DC feedback loop, all the stages are biased using that, assuming it is stable. Okay. So that's why you don't need like separate common mode detection here, which can be advantageous in some cases, right? So no, no, we have common mode feedback for both stages together. We don't have a separate common mode feedback for the first stage here. We don't have anything here. Huh? Yeah, previously we had separate feedback around the second stage and around the first stage. Now we have a single common mode feedback around both stages. Okay. Any questions about any of this fully differential? So signal picture wise, there is not much. So because I won't go into the details, but what will be the differential half circuit of the two-stage op-amp? It's actually quite simple, right? All you have is the differential pair, its differential half circuit is just this, okay, M1 and M3. And following stage also is the same, that's all. M11 and M12, okay. So the first stage gives you, and of course, if you have this Miller type capacitor, that will also be there, okay. So you get GM1 by GDS1 plus GDS3, and then GM11 by GDS11 plus GDS12, okay. Now I don't know if I pointed this out. In a single-ended op-amp, the single-ended single-stage op-amp, because of this current mirror, we have the zero pole, okay. So in the fully differential one, that will not be there, okay, because you don't have these two paths, one of them which has a pole and so on. So that way a differential op-amp, fully differential op-amp has a, I would say, a cleaner frequency response compared to the one that has a current mirror. So basically, you will have mirror pole 0 in the single-ended case, right? Because of two paths adding to the output. Whereas in this case, you will have no mirror pole 0. Okay. Any questions? Any questions about fully differential circuits, common mode feedback, and so on? Now, all the other things, basically swing limits and so on, you can calculate. There is nothing particularly special about it. If you know the bias points and you know the total voltages, you find the thresholds at which you have, find the values at which the transistor goes out of the desired region, either into the triode region or the cutoff, and find the swing limit. So that itself is nothing special. Same goes for slew rate. Slew rate is also related to limits, but current limits. Okay, the slew rate also will be the same. So I won't go through that again, because you can yourself see that if you have this differential pair, the only thing is it will be symmetrical, because in the differential, fully differential circuit, everything will be symmetrical. So this stage will limit the current. So the maximum current that can go into this capacitor and that one, they'll be in equal and opposite directions, but that will be equal to 2 I naught. So 2 I naught will by Cc will be the slew rate limit that you can figure out. But it could also be limited by the second stage. But in both directions, it will be the same. So you can figure that out. Okay. So the slew rate again, I won't deal with. So the rest of the calculations are routine. The small signal and large signal analysis that you know will work. Okay. Now the question is, how do you do noise? And of course, mismatch is the same as noise. So let's again consider just a single stage fully differential op-amp. Right? So now, how do you do noise analysis of this? Single-ended. Now the thing is, you will have, let's say we take noise from M3 and M4, right? Now these are uncorrelated. Okay. So you cannot directly use half circuits here. This is not the circuit is fully symmetrical, but the excitation is not. Okay. So what do you do? Yeah. Basically, that's what you will have to do. This is IN3. This is IN4. Okay. So this can be represented as IN3 plus IN4 by 2 plus IN3 minus IN4 by 2. Okay. Similarly, on the other side, this will be IN3 plus IN4 by 2 minus IN3 minus IN4 divided by 2. Okay. So now, of course, you can do the analysis by, because anyway, this is you do noise analysis with the linear small signal equivalent. Okay. So you can have these two sources first and do the analysis, right? And what will be the output noise? And of course, usually it's only the differential output noise that you are concerned with. Okay, there may be special cases where you are concerned with the common mode noise, but the signal is in the differential part, right? So you are concerned only with the differential component of the noise. Okay. So if you look at these, if you first analyze with this and that, okay, what will be the differential noise component at the output? It will be 0 because this is common mode excitation, and this, by the way, this can be done using the analysis of this part can be done using common mode half circuit. Okay, right? And similarly, the analysis of this can be done using the differential half circuit. Okay. So what will you get as a result? So let me put down the differential half circuit. Or let me put down the both halves of the differential circuit. So now we have IN3 minus IN4 by 2 minus IN3 minus IN4 by 2. Okay. And you are looking at the differential output component. Okay. So now this is a differential circuit with differential excitation, right? So let's say you analyze only this part, okay, and the output turns out to be some Vox, right? Now, what will be the output of the other half? Minus Vox. This will basically necessarily mean that this will be minus Vox. Okay, so this is the idea. You don't need to analyze both parts. Okay. So if this is the case, the actual output VON, what is it? 2 times Vox. Okay. So what is the bottom line? First of all, this source, right? What is the spectral density of that source? So let's say IN3 has a spectral density of SIN3, IN4 has a spectral density SIN4, which of course is the same as SIN3, right? Because they are at the same bias because of symmetry. So what is the spectral density of this thing? So it is, these two will get added up, right? They are uncorrelated. So it will be 2 times SIN3 but divided by 2 square. Okay. So this has a spectral density of SIN3 by 2. Okay. Now you do the analysis with this, and Vox has some spectral density SVOX. Okay. So what is the spectral density of VON? 4 times what? SVOX, because you are doubling the voltage. Okay. So now what you do is the following. You don't have to do all these calculations separately, SIN3 by 2 and then multiply by 4 and so on. So you can simply take the differential half circuit M3. These circuits are, I mean, still linear, right? And you analyze this with whatever noise M3 has, that is SIN3. Okay. And with that, you will get some SVY, let's say. Okay. And the noise in the differential output would be two times SVY. Is this clear? Here, basically, I do the analysis with half the spectral density, and whatever I get out, I multiply by 4. Instead of that, I am saying you just analyze with the whatever spectral density is there. You don't need to multiply this by half. Whatever you get, you simply multiply by 2 instead. That's all. Okay. So this works correctly, but do keep in mind that for noise, you don't have symmetric excitation, right? The noise and the two halves are uncorrelated. It's not like noise is not a differential signal. Okay. But the output will be fully differential if the common mode feedback is working perfectly. Okay. So basically, the end result of all this is you think of the differential half circuit as an independent circuit, you do its noise analysis, right? And you look at what noise comes at the output node and you simply double that, you will get the noise in the differential output. Okay. And exactly same goes for mismatch also. Is this okay? Of course, the answers come out to be the same. I mean, the input referred noise of the single stage op amp will still be 16 by 3 kT, 1 by GM1 times 1 plus GM3 by GM1 and so on. Okay. Because it's the tail current is not going to contribute to noise anyway. But this is an algorithm, but you should also understand the reasoning behind the algorithm. Okay. You analyze the noise of the differential half circuit as though that was your circuit, right? And you just double it. But you keep in mind that this is not the same as, this is not exactly the same as using the differential half circuit to analyze the signal. Then the signals will be equal and opposite. Okay. Any questions here? Common mode? Yeah. So again, the common mode, there can be common mode noise. That is, the two sides can be wiggling in exactly the same way. The idea is the common mode rejection of the following stage will get rid of it. Okay. The entire idea behind differential circuits is you have common mode rejection somewhere. Okay. But it is possible that if you have nonlinearity or something else, or if the following stage doesn't have common mode rejection, the common mode noise here also will have some effect on the circuit. But the idea is we are thinking of this whole chain of differential stages where finally you are somehow sensitive only to the difference. If that is true, then any common mode noise will not have any effect. No, I mean that's the definition of differential, right? So common mode means whatever is same on the two sides, differential means whatever is opposite on the two sides. Right, that will contribute to common mode noise, right? No, it cannot, right? Because it's the same for the two sides. It is like the noise from the tail source. Okay. So it's the noise from the tail source. So basically, it will contribute only to common mode. Okay. Any other questions? Now, we also had derived these feed forward op amps. Okay. Now I'm going to draw a picture of a feed forward fully differential opamp. Right? So how would we go about implementing these? What stages should I use? How would I implement this? Does this any part of this resemble any fully differential circuit that we have designed earlier? Which one? Okay. So if you look at this combination of GM21 and GM22, it is like the two-stage op-amp, right? Fully differential op-amp, except in the Miller case, you have also capacitors across this, but now you don't need that. Okay. So whatever we had for the two-stage op-amp can be used there, the topology wise. Okay. And then we'll have to add GM1, right? So this part is similar to, it is basically two stages in cascade. So let's do that. Again, I'll start with NMOS pair. And now we are sufficiently familiar with common mode feedback circuits. I won't draw that explicitly. I will just show this as CMFB1. That means that whatever your favorite common mode feedback circuit is, you use that to bias this stage. Okay. And it may not even be from this. You can do it from, you can do the feedback from any place that you like. So what do we have here? So this part is GM21. So that part is GM22. Okay. So now what do we have to do with, how do we get GM1? I mean, if I complete this picture, I'll also have that. But how do we get GM1 now? So this is the positive input of the op-amp, negative input of the op-amp, and this is the positive output, the negative output. How do we get the other stage? Where should it connect to? So there are many different options. So one is lots of things you can try to do. One is, of course, you have another differential pair connecting to the output. It can be NMOS or PMOS. Of course, you have to make sure that the bias currents are all adjusted correctly and so on. Okay. So you will have to do this, and this would be GM1. Okay. And this may need additional bias currents here as well. Okay. So this will be the plus input of the op-amp, and this will be the, the other way around. Oh yeah, correct. That is the plus input, and that's the minus input of the op-amp. Okay. So essentially all you have done is like GM1, another differential pair in parallel. Okay. So what disadvantage do you see here? Do you see any? Compared to, we had the two-stage Miller op-amp. Compared to that, does this introduce any disadvantages? What might that be? What was the biggest advantage of the two-stage op-amp? Gain is higher. Okay, here also you have two stages. Gain will be high. Yeah, this probably also can do that. No, first stage, but the gain, the DC gain comes from this one, right? The cascade of the two parts. See, the high DC gain mainly comes from here. Around the unity gain frequency, this is the path that is active. What is another advantage of the two-stage topology that we had? Huh? Bandwidth? Okay. In fact, bandwidth wise, the feed forward is advantageous, right? It's better. Right. Here also you can do that. Because, I mean, you still have only, you stabilize either the first stage or the second stage output. What about the swing limit? Is there any effect on the swing limit? Same. Really? I mean, what has been added here? What is different between this and the regular two-stage op-amp? This part, right? Now, does it have any influence on the swing limit or no? Huh? The input swing is the same, right? You have NMOS differential pair there or there. What happens to the output swing? See, earlier, if this was not there, what is the lowest voltage it could go to, the output? VD sat of this. Now, it will be the input common mode of this minus VT. It will get restricted. Essentially, see, the thing with the two-stage op-amp is, there was no transistor connected between the first and the second, I mean, input and output directly. Okay. So, if you have that, so that was one of the problem with the single stage op-amp, right? So, you could have the input common mode also appeared in the swing limit expression. That was not the case with the two-stage op-amp. Okay, the output could go all the way to 1 VD sat of the supply, all the way down to 1 VD sat of ground. So now this is connecting directly between the input and the output stage. So if you do this, then you will definitely have compromised swing limit. Okay. So this limits the output swing. Now, depending on the swing that you want, you may have to either live with the limit or you may have to do something else. And the other possibilities. Now, given that sometimes, so basically, this feed forward path, the one that connects from the input to output, you need it only at higher frequencies, right? So what could potentially be done is, you bias these, not like this, yeah, you bias these from a current mirror, okay, with resistors, and you can AC couple the input. Okay, you understand? So what happens is, I'm just showing the single-ended picture here. If you had everything DC coupled, okay, so this is GM21, GM22, GM1. And if I plotted the response of these two separately, Okay, later I can add them. What I would get is the part due to GM21, GM22 would do something like this. Okay, so there will be 2 poles and it will do that. And the part due to GM1, the idea is that it will have a much lower gain. Okay, but it would do that. Okay. So now the thing is that the composite one would have done something like that, and around the unity loop gain frequency, it has 20 dB per minus 20 dB per decade slope, and it is stable. Now, which part of it changes if I introduce AC coupling? So what did I do? Where did I introduce AC coupling? I introduced AC coupling over here. Okay. So what happens to the magnitude response or the loop gain here? This is the magnitude of loop gain, right? With AC coupling, which part of it changes? Huh? So basically, low frequency of which one? So it's not that. So this part here doesn't change because that is still DC coupled. Okay. So this part, instead of doing that, it could have done something of this sort, right? It could do that. Okay. But even if it does that, the sum remains almost the same. So it doesn't really matter. So AC coupling could potentially be used here. Okay. So in this case, the swing limit is not affected severely, right? And the other advantage is, if you look here, you had some bias current for the first GM21, some bias current for GM22, and another bias current for GM1. Okay. Whereas here, this is GM22 and this is GM1. They are sharing the same bias current. So that also makes it more efficient. Okay. So if you want to use this feed forward has many advantages for making filters, but it's like I said, first of all, it doesn't serve this as a general purpose op-amp. It's not great for amplifiers with high gain. Okay. Also, it has this type of issues which you will have to work around. Okay. Any questions?